conquering the crypto mountain just to mine some Bitcoin, trading on a network that belongs to no one and everyone, and escaping from a madman's lair by solving complex puzzles. Welcome to the world of blockchain technology. The Bitcoin network is made up of nodes all around the world. These nodes can be created and used by anyone. They are also the key point to the decentralization of the network. So how does this work exactly? To get an accurate picture, we'll have to divide the nodes into three different groups: the light nodes, the full nodes, and the miners. It's important to note that this is an additive succession hierarchy, meaning that the full node can do anything the light node can, and that a miner can do anything the full node can on top of what it can do itself. Let's say we're sitting in a big room and our good old friend Bob comes in. Bob is a light node. In the middle of the room there is a huge whiteboard full of scribbles. Bob walks over to the whiteboard, draws out his marker and starts scribbling away. Since Bob got his boob job done, he's been making some extra money with his escort service, and he wants to transfer this to his mother in India. So he writes the following on the whiteboard. Bob transfers 10 coins to mom. He writes down his signature and sits down. Now at this point the transaction hasn't been sent yet, it has only been submitted to the network, or in this case, the whiteboard. Meanwhile, there is a group of people furiously penning down everything people write down on the whiteboard. They are the miners. The miners are tasked with grouping all the transactions together and create a block to store them in. The blocks are created by solving a complex mathematical puzzle. At one point, Vince, who is one of the miners, jumps up and shouts that he solved the puzzle. But it's easy to just claim that you've solved the puzzle, so it needs to be checked. In the back of the room, two giant doors open and a group of long bearded men in gowns come walking in. They are the full nodes. Simultaneously, the miners are changing into their gowns and join the group of full nodes for their examination. All the full nodes get to examine Vince's solution and the information that he has stored inside of the block. If both of these correspond with the rules of the network, the nodes will reach consensus and the block of information will be added to the ledger. Bob's transaction has now been finalized and the 10 coins are now in his mother's account, directly accessible in India. The whiteboard in the middle of the room is then wiped clean and the process starts over. What we see here is that nobody is in charge of the network and simultaneously everyone is in charge of the network. By definition, this makes the network decentralized. It has no center and no single point of failure. On top of that, the entire network is transparent and any person anywhere with an internet connection can download the ledger and become a node. Inside of the ledger is every transaction ever made for everyone to see. So what exactly is inside these blocks? Each block contains the time that the block is being formed, a puzzle in the form of a target hash for the current block, the hash of the previous block, which is the identification code, and a Merkle root, which is a line of text that represents all the transactions. Let's pause for a moment and have a look at what a hash is. Hashing is the process of taking a certain set and amount of data and running it through a hashing algorithm. No matter how large the data that is put into the algorithm is, the hash produced will always have a preset amount of code. Likewise, every time that you put in the exact same data, you will end up with the same hash. On the other hand, if you change even a single digit in the original data, a completely different hash will be outputted. This makes it impossible to tamper with the input information since it will automatically radically change the outcome. Now, here's the genius part. Since every block contains the hash of the previous block, the blocks are intrinsically linked with each other. It's a chain of blocks, hence the name blockchain. The moment one of the earlier blocks is tampered with, its output hash is changed, which then will lead to the next block having different information in it, namely the output hash of the previous block, resulting in its output hash also being changed. This way, changing one of the blocks will corrupt the entire chain, rendering it unusable. This hashing of the blocks and linking them to each other is one of the key points of security in the network. But that still leaves us with one question unanswered. What the hell is up with that puzzle? We know that a block contains a Merkle root, a hash of the previous block, the timestamp that the block is created, and a puzzle in the form of a target hash for the block itself. If we would put all this information through a hashing algorithm, we would end up with a string of bits, a unit of information that uses zeros and ones. Let's say this string is 1111. Now, this is where the puzzle comes in, because the network has given the block a target hash that it needs to meet in order to be valid. For example, the block will only be valid if the string ends in a number lower than 0100. In this case, our string of 1111 will not be valid and the block won't be created. But how can you meet this requirement if the outcome hash is always the same, if the input is the same? Well, I lied earlier. There is one more component in the block, the nonce. A nonce is an extra number that is added to the input to change the outcome of the hash. Since the outcome hash will change completely by even the most minor of changes, every time the nonce is changed, you get a chance of hitting the required target outcome without changing the relevant data inside the block. Since the only possible outcomes for bits are 1 and 0, we have a 50% chance of hitting either one. If we were to try a different nonce and hash our block, the chance of starting out with a 0 would be 50%, and the chance of starting out with 2 zeros would be 25%. So in the case of our 0100 target hash, we would need to try 4 different nonces in order to statistically have a 100% chance of guessing the right output. Imagine being in a big cave and there's 2 paths you can take, right or left. One of the paths will lead to a painful and miserable death, and the other leads to fortune, fame, and happiness. The only problem is that you don't know which path leads where. But you have to make a choice, so you decide to take the left path. In this case, you would have a 50% chance to die and a 50% chance to live. But unfortunately, the crazy lunatic that locked you in this cave changed the rules. Now you have to choose between the 2 paths, only this time one of the paths leads to your agonizing demise and the other path leads to another cave. In this new cave, you have to choose again between life and death. If you were to choose the left route again, you have a 50% chance of living or dying. Let's say you live and you get to the next cave, and here you choose the left path again. You once again have a 50% chance of living. In total, however, you only have 50% chance of 50%, bringing your odds down to 25%. Now shit gets real nasty. The crazy man's father comes in and decides to show his son what a real challenge is. He locks you back in the cave, but this time you have to pass through 40 consecutive caves, with each one of them having a 50% chance of killing you. The odds of you choosing the right path every single time would be 1 in a trillion. Good luck. But this is the extent of which the puzzles in a block are formulated. Every extra 0 that is added at the beginning of the target outcome will double the difficulty of finding the correct input. And since the hashing process is a one-way street, which means it's impossible to use the outcome hash to find out the input data, the only way to find the correct answer is to try a whole lot of different inputs. And that's what we use the nonce for. That's a lot of information to process. For now, we'll close the book of blockchain land, but next week we'll begin a new chapter looking at why a puzzle is necessary, security risks of the network, and how to create your own Bitcoin wallet. Thank you so much for watching this video. If you enjoyed this content, don't forget to join the pack by subscribing down below. Now, let me show you this cave over here.